Então, sejam bem-vindos à aula inaugural do nosso programa de pós-graduação em Engenharia Elétrica e do programa profissional em Engenharia Elétrica, né, PPGE e o PPE, com apoio da I3E, do nosso chapter aqui da UNB, VTS. Né. Nós hoje temos a presença do ilustre Sandip Kundu, um pesquisador aí na área de redes, de microeletrônica, de segurança, né? Quem tiver alguma pergunta, ele prefere que seja feita durante a apresentação mesmo. Então, sintam-se à vontade para levantar a mão e fazer a pergunta que vocês tiverem aí durante a apresentação, tá? Então, né, vamos começar. Eu vou mudar agora para inglês, né? Então, I will make a brief introduction. So Sandip is a professor of electrical and computer engineering at the University of Massachusetts, Amherst. Yeah. He's currently on leave from UMass, serving as a program director at the National Science Foundation. Yeah. He worked in Intel and IBM, several big companies. Yeah. His research interest includes security of mobile and embedded devices, computer microarchitecture, VLSI circuit design and testing, computer-aided design algorithms, and information encoding theory. Yeah. So, Professor Sandip Kundu, we are very honored to have you here with us today. So please, let's start.
So thank you, Alexandre, for the introduction. I hope those of you in the back can hear me. Can you please raise your hands? Good. All right. So I'm going to be talking about security and privacy concerns that come up with machine learning algorithms. And the concerns that I'll be talking about are primarily from the engineering point of view, not necessarily from the sociology point of view, because there is a whole lot of concerns there as well. So machine learning has been, is becoming ubiquitous in many aspects of life. In fact, So, in the economic sphere, people have expressed concerns about what happens when machine learning becomes deployed in industrial scale for doing routine cognitive functions. And of course, this has been called as the fourth industrial revolution. That's going to transform the way the humans and the society is organized. So the first industrial revolution had to do with development of the steam engine, and which basically saw that transportation system developed rapidly, making it possible for people to travel long distances by ships, by trains, etc. The second industrial revolution was led by electricity, where the electrical appliances and machines and motors, they made industrial production much easier. It basically substituted, allowed us to replace human labor with labor done by machines. The third industrial revolution had to do with industrial automation. So we found that more and more factories are being automated, and many of the routine production tasks in factory are no longer done by humans, but rather they're done by the machines. With machine learning, it's expected that many of the routine cognitive tasks that involves thinking, that involves sort of pattern recognition, will be now done by the machines. So clearly there are concerns for the economists that what it means for future jobs and how will people organize their workplace, what will humans actually do. But that is not the subject of my talk today. I'm just here to talk about some of the engineering issues that arise from wide-scale deployment of machine learning. So some of the applications where machine learning is finding new frontiers. One of them is self-driving cars. The self-driving car, even though as defined by Automotive Society of Engineers, they have defined like various stages of self-driving car, level 1, level 2, level 3. And we are pretty much at level 3 today, where the cars can do a lot of the driving by themselves, but it does require some sort of human intervention. And within a few years, we'll be in level 4, 5 and beyond, where no human will be necessary for driving or navigating a car. So most of the pattern applications that happen in self-driving cars is you want to identify the scene that where you are in, which is basically known as perception, where you like to recognize the pedestrians, the street signs, the walk signs, the traffic signals, any change in the road conditions such as a policeman redirecting traffic. So all of that perception is going to be done by machine learning system, or is already being done by machine learning systems. Another application is in cybersecurity. Today, when you get your email, machine learning tools automatically do a lot of the spam filtering. The spam emails that you get, they're eliminated by many of the machine learning tools. And of course, for those of you who use private email services from providers like Google or Facebook or others, you have experienced that they do a pretty good job of eliminating most of the spams. There are other applications such as in healthcare. In healthcare, the big thing going forward is going to be personalized healthcare, because the physicians recognize that people may have identical medical conditions, but when they're given medicines, they respond very differently. So why do they respond differently? And based on all sorts of medical data that has been collected over the years, now we know that based on your several parameters like say your DNA factors, your age, your ethnic background, etc., we can actually tailor a medication that will be more effective for that patient compared to just giving some medication that seems to work for the general population. There's a lot of application of facial recognition that's already coming in, and a lot of application of speech recognition. So these are some of the applications, and maybe I'll expand on that a little bit later in the future slides. But let's just get to the engineering core of how the machine learning works. So at the core of it, you have a lot of training data, and most of that data for machine learning to be usable, they are curated, they are labeled. So for example, if you're going to be doing self-driving cars, and one of the things that these companies do is they fit the cars with cameras and other sensors such as lidars, radars, and then they drive the car around. And once you get that footage of what the various things that was observed by the car, a human has to manually go and label things, that this was a stop sign, that was a pedestrian, this was a car parked on the side of the street. And once you have done the labeling of the data, then you can give it to a mathematical tool, which will then try to build a model such that in future, if you feed an input, it will automatically be able to do classification and make decisions. And so it will know that it's a pedestrian who's about to cross the street. So in machine learning, one of the big foundation is providing training data that has been appropriately labeled. And then of course, That leads to all sorts of other issues which I'm not going to talk about, but I'll just maybe say a couple of sentences to make you aware of some of the problems. If the training data is biased, then the machine learning decisions can also be highly biased. And this is a concern for economists and social scientists. For example, people submit loan application in banks. And in the loan application, if you look at a bank's history, there are forms that people have filled out. And at the end, a loan officer made a decision whether to give loan to that person or not, right? Now, if you want to replace the loan officer with a tool, such as a machine learning tool, then you will take all the past loan applications, and the data is already labeled, whether the loan was approved or not, and you train a model, and the model learns from the past data as to what kind of application the loan will be approved and which kind of application the loan will not be approved. And what happens in that case is once the training has been done, the human can be replaced by an automated tool that receives your loan application and decides whether you get the bank loan or not. A lot of people have pointed out that in the past, many of these loan applications were highly biased. For example, they might have been biased against people of color, such as in the U.S., that would be African Americans, having identical loan application, they might have been denied loan simply because of their skin color. And if you have trained a machine with that kind of data, the machine learns that behavior and reproduces that kind of a behavior. So that is a concern for the sociologists. So we are not going to be talking about that, but it's a whole new aspect of what kind of data do you train the machine on. So let me talk more specifically about some of these examples, and then later I will go into the security and the privacy concerns. So in a self-driving car, for example, here's a stop sign on the road. There's a camera which may be mounted on top of the car. The camera picks up this stop sign. So the first thing that has to happen is we have to recognize that this is a sign. And so there has to be some kind of a pattern identification tool that it identifies that this is a road sign. And once it figures out that this is a sign, it will be fed to a classifier. And the classifier then looks at the sign in details, and it goes through a neural network, which is typically a convolutional neural network. It's given the input, and then at the end it makes a decision what kind of a sign it was. Was it a stop sign? Was it a yield sign? Was it a turn sign? And so on and so forth. So at the end of this process, what we have is first we do some kind of a image detection, and then we run image classification. So those are the two steps in order to figure out what kind of image am I looking at. So again, in terms of self-driving cars, what happens is as far as the software is concerned, there are only 4 important components. The first component in a self-driving car is the car asks itself, where am I? Like, what is my current location? And it can derive the current location based on the GPS data, which is effective most of the time. But if you're driving in a major city like New York City with high-rise buildings, then the GPS signal is not very good because the signal is blocked by the tall buildings. So in which case, you'll have to resort to other kinds of information to figure out where am I. And it could be an inertial system, it could be a system that searches to the image database and looks at the buildings around and figures out that this is my location. So that's the first question the self-driving cars ask is, where am I? The second question that self-driving cars ask is, what's around me? So I'm at this position on the street, and what am I looking at? So I'm looking at a vehicle here, I'm looking at a human there, I'm looking at a sign there, I'm looking at a traffic light there. So that's the second question, is what's around me. The third question for a self-driving car is the things that are around me, what are they doing? Like if there's a car parked on the side of the road, is the car just staying there or is it pulling out? Uh, it was parked, but now it's joining the road. If there's a pedestrian who's on the side of the road, is the pedestrian waiting or is the pedestrian about to cross the street, right? So that basically requires dynamic information. You do the scene detection and then you figure out that what are these entities doing. And in the fourth phase, then you figure out that that the entities around me, there's a car which is parked on the side of the road, is just pulling out. There's a pedestrian who's about to cross the street. There's another car which is cutting me in the front. And so based on that, you figure out that this is the space within which your car will be safe. And within that space, within that box, you try to figure out that based on my current direction, my current speed, and the condition of the car, what do I need to do? Do I need to accelerate? Do I need to apply the brake? What exactly control actions are required? So those are the four stages of a software in a self-driving car. And out of which the first 1, 2, and 3 relies heavily on the machine learning to figure out where am I, what's around me, and what are the objects around me, what are they doing? So those 3 questions are heavily answered by machine learning system. Here I'll give you application of machine learning in healthcare. Now this was a paper from these people. They basically develop a tool by which you take very high resolution images of human skin when you have a skin disease. And then they train a machine learning model, and at the end the machine learning model, once it has been properly trained, you can take a picture of skin condition and it can tell you whether you have a cancer or what kind of skin disease do you have. So this is something that was reported, which is an application of machine learning. Another application would be actually in drug discovery, where the chemist can look at a structure of a molecule that you're trying to destroy and figure out what other kind of molecule that I need to construct in order to be able to destroy this structure. I already talked about personalized medicine, so I will skip on that and maybe just talk a little bit about cybersecurity. So in cybersecurity, there are 2 sets of people. One is an attacker who's trying to spam you, and one is a defender who's trying to protect you against the scammer, against the people who are sending out the spam. So if I'm developing spam, and I know that Alishantri uses Gmail, and I want to be able to send him a spam defeating, say, all the defenses that Google has built for spam detection. What I'm going to do as an adversary, I'll first open a whole bunch of bogus Gmail accounts, okay? And then I will construct an email, and I'll send it to one of those accounts, and I'll try to see if that account receives that email or not. If that account has received the email, then I know that that email is passing through Google's filter. If, on the other hand, that email didn't make it to my bogus account, I would know that when I sent my email, it was filtered out by Google. So in the process, I have an input and I have an output. The output says whether it went through or not, and an input is something that I'm crafting. And at the end, my task as an adversary is to craft an input which will defeat the spam filter that, say, Google builds or Facebook builds or Microsoft builds. And if I can construct such a spam, then I can take that bogus email and I can send it to a large number of people because I know that I have defeated their filter. And what are the people who are building these filters doing? They are looking at spams, because as soon as an email comes in, there are users who are labeling this as spam, and that is being used to train a machine learning model. And that machine learning model is continuously refining itself so that over time it just gets better, and now you have a game between the adversary and the defender. The defender is trying to build a better model so that you can filter out all the spams. The adversary is trying to figure out the model that the defender has so that I can build a spam that will pass through the filter, right? And this kind of tells you that in machine learning, when you use a pattern recognition tool like that, at the end you have an adversary who might have financial incentive, who might have other incentives, so that you try to defeat the machine learning system and you can make it do bad things. And that's where I'm going with the presentation. So I will outline a couple of more applications before I move on to the engineering part of it. So facial recognition is also being widely used. For example, Apple uses a Face ID that allows you to unlock your phone by looking at your face. Criminal identification, a lot of the police systems, they use a picture from which you can search through all the image database and quickly identify whether you know about this person or not. So that's as far as the government is concerned, or some of those businesses are concerned, but there's a lot of customer personalization and specifically targeting advertisements that goes on into this space where they do facial recognition. So one of those, I will jump here, is augmented reality. And the augmented reality is used in retailing, like by the online stores. So for example, you walk into a store and there's a camera which is looking at you, and it automatically collects your body profile as to what your height and your body shape, etc., etc. And then without you even trying on the dress, through augmented reality, they basically tell you what you will look like if you put on this dress, right? So all of this involves some kind of a recognition system. And of course, many of these recognition systems, such as text, language, etc., there's automatic translation, like you can use in your phone an application that can look at a sign and automatically translate that. And it also integrates with geotagging. So these are some of the applications that are developing quite rapidly. In one of those companies which are doing ad targeting, has developed an app by which you walk into a car dealership and they take your picture using a camera at the car dealership, and immediately goes into a recognition system to identify whether you're a man or a woman. And they also identify what is your age, because the age, figuring out your age from your image, that has become fairly accurate these days. You can pretty much point out by using a machine learning tool that this is your age within plus or minus 1 year or so. So once you have taken a picture, you can profile that person, and based on that profile, you can start targeting advertisements, which is one of the big applications that is being developed in the commercial sector. And there is also a lot of applications of machine learning in speech recognition. If you look at, say, Apple's Siri or Google Assistant or Samsung Bixby, all of them, they can recognize your speech with in-home automation, Amazon's Alexa, IBM Watson. They're being used for translation, transcription services. There's a concern there as well, because not only they can recognize your speech and automatically transcribe, but more and more it can also do identification of who the person is. So for example, if I talk to my phone and my phone has collected my voice sample and it has trained, then eventually when I call my bank and the bank asks me a question and I answer it, from my voice detection, they can automatically tell who's calling. Okay, so this is, they can, and the accuracy these days is almost like 1 out of 1 billion kind of a specificity, by which you can automatically, by listening to somebody's voice for 15 seconds, you can tell who the person is. Not just what the person is saying, but who the person is. So that's a significant privacy concern, but again, this is not what this talk is all about. So next, I'm going to be switching gear and talk a little bit about machine learning security and privacy issues. So let's look at something that I already described, that the first phase in machine learning is data acquisition. You need to acquire the data, and then the data preparation by which you label the data, and then you go into the model training phase, and you train a model, and then you go through a model testing phase, where you test how good your model is in classification, and then you go into the deployment phase. So out of all these phases, this is now becoming more or less standardized. So if you actually have lots of data, and if you open an account in Amazon, for example, in AWS, you can use their tool to automatically build this model for you. So you don't have to do the model, you just apply the data and they'll build the model for you. And the same thing, there are tools like that available from other internet providers, cloud service providers such as Microsoft Azure and Google, et cetera, even IBM. They all have the tools where if you take your data, they will automatically train a model, and then they'll create a model which will allow you to then do all sorts of classification testing. So this process has become so automated, and that a lot of the companies don't actually have to know the engineering aspect of how this model is being built. They just need to go through the menu and choose what kind of a model they want. Do they want in a deep neural network, and they have to select the hyperparameters such as how many nodes, how many layers, et cetera, et cetera. And these days there are tools that are even doing the task of choosing the hyperparameters for you. If you just apply the data, everything gets built. So what are some of the security and the privacy concerns there? So the machine learning algorithms in real world, they mainly focus on two things: accuracy and efficiency. So in terms of accuracy, it just means that how accurate am I in terms of recognizing or classifying things. And the second question is, how efficient am I? What is my model size? Is my model, will my model fit within hundreds of kilobytes, or do I need hundreds of megabytes to fit my model? So that has to do with model size. So just to pick a specific example, if you talk to Apple Siri, and if Apple Siri does not recognize what you're saying, that's an accuracy problem. And suppose you fix that accuracy problem, and by training with lots and lots of data, and then you might have a blow up in the model size, and so that next time when you speak, it not only recognizes you correctly, but it takes a while before it can do all the processing because the model is too big. And that has to do with efficiency. So there our question would be that how small can I get the model so that the model actually classifies fairly accurately, while at the same time has a low latency, so that when I ask the question, it comes back with an answer very quickly, and has all these attributes of lower power, and it doesn't consume too much of my battery power if the model is going to be sitting on my phone and things like that. So this is just one aspect of it. The other aspect of it is that there's a whole bunch of applications that are developing as machine learning as a service. So the businesses are still trying to figure out how we can make money using machine learning and providing that as a service. So I'll give you an example, and I have that in a slide later on as well. So there is the largest cancer hospital in New York City, the Sloan Kettering Hospital. They have collected lots and lots of data on cancer patients over many years, where they have the medical images of the cancer, the radiological images, and at the same time, those images have been labeled with what kind of cancer it is, because if a patient dies, or even if a patient is alive, sometimes you take a tissue sample and you study under a microscope to figure out what kind of cancer it is. So now you have an image, and you have another test, a histological test or test on the cells, that tells you what kind of cancer it is, and you can label the image. Once you have done that over, say, 40, 50 years, you can take all of that data and you can train a machine learning algorithm. So that now if you take a radiological image and if you feed it to this model, it will tell you that it is this kind of a cancer, okay, with certain accuracy. Accuracy can be fairly high because in this case, there's a large amount of data which is available. So my question to you as an audience is, suppose I'm the hospital and I have this data, and a startup company comes to me and says that, may I have access to your data because I want to build this model, and the startup company doesn't really have to do too much work other than taking that model, pre-processing it to fit certain format, and then use one of the web services tools such as Amazon or Google, whatever. Out comes a model which will do the job. Now this company then takes that model, and what is the company going to do with the model? They will then sell that model as a software tool to the various doctors in the hospital, so that now the doctor has a tool, you feed in the image, and out comes the report. In this process, who should make money out in this business? So my question to you, that who should make the most money? Maybe everybody makes a little bit of money. Who should make the most money out of this business? Who? The data owner. Yeah, because most of the intellectual property was actually in labeling the data. That was where most of the work went on, right? And of course, the software developer who just packaged all of this should also make some money. And once I create the model and I'm selling copy of the software tools, right, the doctors whose job I have automated, I've improved the doctor's efficiency. Now the doctor is able to scan through lots of images very quickly and come up with results. And as a sanity check, doctor can look at the report generated by the machine, look at the image, and based on his training, the doctor say, okay, this looks good, right? Now imagine that, suppose that has been done, and I'm an adversary, I'm coming in, and I bought one copy of your license, okay? And after I buy one copy of the license, the model is secret, because the model itself has lots of parameters in the network, and I bought one copy of the license. And my goal is, I'm not a doctor, I just got one copy of the license. My goal is to reverse engineer the model. If I can figure out all the internal parameters of the model, then I basically broken two parties in the system. The hospital which generated all the data, did all the work, suddenly that data is available to everyone because somebody has reverse engineered it. The software company that did all the work in packaging it together, they got to sell one copy, and then after that everybody figures out how to reverse engineer. That would be a problem. So this is one of the issues that I'm going to be talking about. So what are some of the attacks that are possible on a system? So first attack is confidentiality. I can extract the model parameters or the private data that the model was trained with. And it turns out that the mathematics behind extracting the model is not all that complicated. Okay, and I'll show you some results there. The second type of attack is an integrity attack. In an integrity attack, what happens is I have your model, and your model may be fairly accurate, but I can figure out, having one copy of your model, that how to defeat your model so that your model will start doing bad things. Okay? And I'll give you one example, and this was already published and it made big news. This was research done at University of California, Berkeley, where they basically trained a machine learning model to recognize the various signs such as stop sign, yield sign, right turn sign, etc. So the model was trained with all sorts of data. Once the model was trained, then the researchers, they're trying to figure out what is the smallest change I can do to the model so that my model will misclassify. So you take a stop sign and then you start changing pixels of the stop sign, one at a time. And then you try to see how well the model is doing in terms of classification. And you're trying to do minimum amount of change so that the model will no longer call it a stop sign, it will call it something else. And by doing this research, what they found is that once the model has been trained, if you take a small sticker and place on few locations of the stop sign, then the model classifier is going to misclassify the stop sign and is going to think of that as something else. Okay. So once you know that, so once you have a copy of this machine learning model, I can craft what are known as adversarial inputs. The adversarial inputs are inputs that's going to defeat that machine learning system. And once I know what those adversarial inputs are, I can then start making those small changes, and the system is going to crash. So for example, if I knew that somebody was going to drive through this road, I could go and take some yellow stickers and I could put in few corners of the stop sign, which no human being is going to be fooled by that, will recognize that as a stop sign. The machine is going to be fooled by that, and the machine is going to simply run through the stop sign and will create an accident. Okay. So that's an adversarial input which causes an integrity violation. So it compromised the model to produce false positives or negatives. There are also availability issues which can make the model unusable. Now, in terms of attack influence, it could be exploratory, which is find and exploit problems like the example that I gave you. It could be causative, which could manipulate the training data directly so that I know that this data is going to be misclassifying at certain times. The attacks could be very specific, or it could be indiscriminate attacks where I just want to attack the system and I don't care, how things happen. So I already talked about the security and the training process, that you first get data, you label the data, train the model, test the model, deploy the model, and I can do confidentiality attack on these bars, and the integrity attacks here, availability attacks somewhere there, and I'm going to go through some examples and talk about this. So training data confidentiality. Training data is valuable, like the example that I gave in terms of the cancer hospital. It's actually a Sloan Kettering hospital worked with a startup, and the big question was, who owns the intellectual property? Is it the hospital who owns the intellectual property? Is it the company that owns the intellectual property? So that is a big controversy. But having said that, these data should remain confidential. But if I can reverse engineer and figure out what the data went in creating the model, then you have a problem. So there are people who are putting lots of work in collecting data sets. Data annotation, data curation, and data privacy is absolutely critical. Also, ensuring training data, the confidentiality is also very critical. So there are different types of attacks that people have created in order to breach the confidentiality of machine learning model. One of them is known as model extraction attack. Extract the model parameters via querying the model. And the other one is model inversion attack, extract private and sensitive inputs by leveraging the outputs and the inputs. So I will give you specific examples of that. So let me just, for the sake of this, go directly into an example. So here's an example of a model inversion attack. And for those of you who use Facebook, you know that in Facebook, if you label the name of the person, then Facebook learns the name of the person, and then later on Facebook can automatically, once you take a picture, can put a label who it is, right? And so Facebook has created a model that given a picture, it can output the name and it knows who the person is. So in this case, suppose an attacker has access to the model, but the attacker does not know what the people look like. Okay, and suppose the model was trained with all sorts of pictures, and say here is this person named Fredrickson, and the model was trained with Fredrickson. I don't know what Fredrickson looks like. So what I do is I have access to the model as a black box, and I start with a clean slate, and then I keep changing one pixels at a time until the model tells me that this is Fredrickson. So what I have done is I didn't know what Fredrickson looks like. I had a black box model which was available to me that was capable of doing the classification, and I learned what Fredrickson looks like from the model. Okay. Why is this picture a little hazy and not as clean as this one? So one of the things that I mentioned in the beginning is that when I create a model, my goal is also to achieve efficiency, right? So if you give me an ultra high resolution picture, maybe I don't need a very large model in order to classify things accurately. So I build the smallest model I can. So when you invert the picture, you are not going to get a precise picture. You will get a better picture if I allowed my model size to become bigger and bigger, right? But one of my optimization goal in creating machine learning model is that my model should remain small. And if it remains small, then I'm going to have some loss of accuracy in the inversion attack. But if I allowed my model size to become very large, I will not have that loss of accuracy. Okay, so for all practical purposes, we don't really care because we more or less know what the person looks like. Given that we had a black box model, and I started with plain input, and I started changing the input a little bit at a time until it changed the name of the until the model told me who it was. Exactly the same thing goes. Here's another publication that looked at medical diagnostic data. And suppose a patient has some kind of a medical condition, and you happen to look at the person's medicine cabinet, and you find out what medication this person is taking. If it was personalized, then you can figure out all sorts of private information from the model that you're not supposed to know. So here's another paper. And one of my visitors, he's actually a Brazilian, who's working with me, he was working on how to build models that you cannot invert, where you cannot run model inversion attack. So one of the things that he came up with is that if we add a small amount of noise, random noise, to the model each time you query, then depending on how you craft this noise, you might be able to defeat the model inversion attack. And here's a demonstration of that. So this is the person whom we are looking for in a model inversion attack, and these are the iterations that are taking place on a model. So as you can see that as these iterations go, that once we add a small amount of noise, then in one case the iteration does not converge, and in the other case the iteration converges. And so in this case model inversion attack is more or less successful, but in this case the model inversion attack is not successful, depending on where the random noise has been added. And eventually the adversary is not able to create a complete adversarial input. So I will next talk about the integrity issues in machine learning. So ensuring integrity of a machine learning model is very difficult. It depends on the quality of the training, the testing data set, etc. It also depends on model sophistication, whether it is a small model or large model. It also depends on lifetime management, etc. So I will just go through some examples without trying to show you what these problems are. So there are two types of integrity attacks that we worry about. One is poisoning the model itself, and the other one is getting the model to do getting the model to misclassify things. So in the first case, we are doing something with the training data so that the model itself which is created is bad, and in the second case the model is not bad, but we are using the model to do bad things. Okay, let me give you an example of the first one. How many of you have used navigation software while driving a car that is phone based, such as Google Maps, right? Google Maps, if you use, is able to tell you the traffic condition on the road. It changes the color, and if there's a heavy traffic, it tells you that, changes the color to red. How does it know that where the traffic is? Any navigation software, how does a navigation software know where the traffic is not moving? So if lots of people are using that application, not only you are getting navigation information from the software, but the software is also learning the speed at which you're moving, right? And the speed at which you're moving then is telling the software that this road, there's a lot of traffic. And it's using that information to maybe even reroute and take you through a different road to the same destination, okay? So imagine that in this case, how was the model created? By doing some kind of a crowdsourcing of the data. So there are lots of users, and you take the data from the users, you figure out what the condition on the road is. Now, suppose I'm an adversary, okay? So what I do is I collect 100 phones from my friends, and all of them I open, the map application, and then I go and park my car on the side of the road with all this application on. So all of them are telling this model that they're not moving. So what will the model learn? That the traffic in this road is busy because the cars are not moving. Okay. Some are moving, others are not. So when you statistically average things out, they're mostly not moving, right? And in which case, what will the software start doing? It'll start rerouting you, right? And that's a form of attack on a system. So anywhere where you're doing crowdsourcing to mine information, I have a fairly easy pathway to poison the model. And this is a poisoning attack where I'm feeding data to the model that basically says that the model goes bad. I'll give you another example. On the self-driving car software, what happens is the car the software gives you a recommendation as to what you're supposed to do, but then there's a driver, and the driver is actually in control of the car. The driver can override the decision, okay? So whenever you override the decision, the software collects that input as a trace, and eventually when you have large number of such traces, you're able to retrain the model, and the model becomes better, right? So supposing I'm a company, without saying any names, let's say I'm a company which is producing expensive car that runs on batteries, and then it has some self-driving capabilities. And each time you take the car to some dealer for servicing, they can download the data as to where you overrode the car software, and based on that they can retrain the car. Now imagine if the car, based on the traffic condition, gave you an input to apply brakes, and you overrode the decision by pressing the accelerator, and you are doing that in a adversarial environment where you're basically looking at the recommendation being given by the car, and you're always overriding it. So what does the car learn from you? Eventually it learns that in that situation I must accelerate and not apply the brake. So because this was done with adversarial setting, and one of the adversarial setting could be, instead of having real objects, I could have picture of Alexandre instead of having Alexandre in there. And so it's a completely adversarial setup in which I'm inputting data. And because a lot of it is just based on crowdsourced data, the machine is learning bad things, and it starts doing very bad things. So that's a model poisoning attack. Model evasion attack is I have the model, and from which I learn when will the model make bad judgments. So here is again an example which was generated by my Brazilian visitor, Tiago. So this is from a set of benchmark. It's called the CIFAR 10 benchmark suite, which has a lot of images. And based on the image, you train the model, and the model learns to classify things accurately. So then what we are doing is, if you take an image and you blur the image, and then you see that when the model classifies it accurately, so this is still being classified as dog. And in this case, we are mounting a targeted attack. So we want this the dog to be classified as airplane. So what we said is we developed a piece of software that keeps changing the pixel values in this dog by using an algorithm which is called the gradient ascent algorithm until we have the smallest amount of change to classify the dog as an airplane. Okay. So now the machine learning software is fooled. It looks at a dog, and because I changed some pixels, and as you can see that I added some white spot here, and I figured out exactly where to add this noise so that this dog is now going to be classified as an airplane. Okay. Now, why is this a problem? So I have a model which has been trained, and I'm using that model as a black box, and I'm playing with that model, changing input until I figure out the model is misclassifying things. Okay, and I'm doing it in a targeted way. Why is it a bad thing? Why is it a bad thing? So imagine I'm a manufacturer of a camera. Okay, and so suppose Sony makes the CCD sensors, and I collected images from a Sony sensor, and then the model was trained, etc., etc. What I can do is I can buy the CCD sensor from Sony as an adversarial attacker. I can craft a camera where the camera itself I add the noise, okay? And when I sell you the camera, you look at the camera output, visually you can't tell the difference, but the camera is already bugged, okay? And so that when you install that camera in your self-driving car, it's misrecognizing things. And because I was able to have a copy of the software, and I was able to figure out that if I made these specific changes in these places, it's going to be doing bad things. So I can already do that where visually looking at the camera image, you can't tell the difference, but when you couple that with the machine learning system, it begins to do bad things. So all I have to do is, if I want you to get into an accident, I have to go in the middle of the night, remove the camera from your car, replace that with a different camera, and then you're doing self-driving navigation. It's working perfectly okay, 99.99% of the cases. But that one case for which I bugged your car, you come across that situation and you have a targeted accident. So here was that example that I was talking about, that a model was trained with different types of stop sign, because when a camera is looking at it, it may not be looking at the perfect picture. It could be at an angle. It could have displacement. It could have different lighting conditions. So this is how the model was trained with. And here what we are doing is we are adding some things, and we just find the smallest perturbation so that the model begins to do bad things. And all of this involves a heavy amount of mathematics, and I'm not going into the mathematical part of it. I'm just telling a general story as to how it is done. So in this case, it's a post-training phase attack, and it already has some knowledge of the neural network model. It's a black box model, and it basically does some kind of a adversarial perturbation to defeat that, and again it's based on algorithm called gradient ascent algorithm, which eventually defeats these kinds of models. We can do similar things against automatic speech recognition. So let me not read the slide and let me just give you a story. This was a paper which was published in a security conference 2 years ago. So when you use a phone microphone and you speak to it and the phone does your speech recognition, you can tell your phone, for example, Siri, what's the weather in Brasilia today? And it'll tell you the temperature and so on and so forth, right? Now in this particular case, what they did is they crafted adversarial inputs. The human ear has an audible range of about 20 hertz to 20 kilohertz, right? But the microphone, which is in your phone, can hear things which is beyond 20 kilohertz. So in this case, they crafted an input which is in the ultrasound spectrum. So you are sitting in the room and somebody played that ultrasound noise, okay, which you couldn't hear, but the microphone in your phone could hear, and it was recognized by that software system, the automatic speech recognition system as a command, and your phone did some things which was like really maybe embarrassing to you, such as telling you some dirty things in front of your kids, just because somebody put an adversarial input which was in a different frequency band, which was not even audible to anyone. So this was an example which was created. And so as you can see that this is a real challenge from the engineering perspective. How do you develop models for that are resistant to adversarial input crafting? Okay. And lastly, I will talk a couple of slides about availability. So in security, you worry about three things. Confidentiality, that is my data must remain confidential at all times. And the examples that I gave you that I was able to exfiltrate the data, such as I was able to learn what somebody looks like and somebody's medical data. So that is like leaking all sorts of information which are supposed to be confidential, and so it's violating the privacy. The second example I gave you was integrity violation, where you have a model and you get the model to do bad things. Okay. So in the first case, you have a confidentiality problem. In the second case, you have integrity problem, and this is the last case where you have an availability problem. The availability problem, simply stated, is that your model does all sorts of things, but if I get your model to take much longer to respond than normal expected latency, in a real-time system, that's not very useful, because if I'm driving a car, I need to know, the behavior of the car in real time, what I should do, and model is telling me the right thing, but it's taking a long time to respond, and in which case I get into an accident anyway. So that's like one of the attacker goals, is to degrade the learner's performance, and we can actually craft input in which case it will do exactly the same thing, that right thing, but it will take longer than necessary to do the right thing. So I'm crafting input so that the model is still doing the right thing, but it's taking much longer to do the right thing. And therefore, by degrading the performance, I can mount an attack, because you're getting the correct decision, but you're getting it too late. So in conclusion, machine learning applications are proliferating rapidly. The business service model is also evolving rapidly, but machine learning has multiple security and privacy challenges. It has problems with training data and model leakage. It has problems with adversarial example crafting. It has problem with model poisoning, and we need defensive solutions. Most of the defenses today are not robust, and solutions also involve certain amount of cost. So for people who are involved in machine learning, this is an important area of research that, in the first phase, we basically build capabilities assuming that these capabilities are useful. And of course they're useful, but then it attracts all sorts of adversaries who are trying to defeat the system. And the next phase, we'll have to build machine learning system that can withstand all these attacks. So that's the next frontier of research. So thank you, and I'll be happy to take a few questions.
So any questions from the audience? If you want, we can translate your question also. If you, a gente pode traduzir, né? A gente pode traduzir a sua pergunta. Alguma pergunta? Sim, não? Okay, so I just have one quick question. Like when you showed us that picture of Frederick, that you changed some pixels to produce his face from nothing, right? How long does it take? Like, what is the processing need that you had for this kind of attack?
So the processing is relatively simple because your model has been trained with all sorts of people. So let's say your model was trained with 100 people, and I'm trying to figure out what Alexandre looks like. And so I first feed a picture, and this picture is not classified as anyone, say correctly, but the machine learning model assigns scores. And so it says, the score is 30 for being Alexandre, score is 35 for being Sandip. And so I have this set of scores. So now I'm doing a gradient ascent. I change some pixels, and I want Alexandre's score to go up and all other scores to go down, right? So how would I craft an input? So